All right. So far, we've been talking mostly about how experiments are designed. Now let's zoom out a little and talk about studies more generally. Here's the reality. In most situations, we simply can't study everyone. It would cost too much. It would take too long. And sometimes it's just not possible. So instead, we study a sample, a smaller group that we hope represents the larger population. And here's the important part. How we choose that sample matters enormously. A good sample can give us useful information about a population. A bad sample can give us a completely misleading picture. So in this section, we're going to get practical. We're going to learn how samples are selected, what makes a sample good, and what can go wrong when the sampling process is poorly designed. Let's learn how to sample well. Okay, before we get to sampling, I want you to notice something else. Studies can also differ based on when the data comes from, and that timing affects what the study can tell us. There are three main types here, so let's take them one at a time. The first is retrospective. That word basically means looking backward. In a retrospective study, researchers use records or information that already exists and look back into the past for patterns. Look at the example on the slide. In 2019, there was a sudden outbreak of serious lung injuries connected to vaping. Investigators looked back through hospital records and patient histories, trying to identify patterns and possible causes. The big advantage of a retrospective study is speed. The data already exists, so researchers don't have to wait years to collect it. But there's also a downside. You're relying on old records, and sometimes on people's memories. And, as we all know, human memory is not always perfect. The second type is prospective. Prospective means looking forward. You choose your subjects now, and then follow them over time to see what happens. A classic example is the Framingham Heart Study. It began in 1948, and researchers have followed participants and their families for generations. Studies like this helped researchers identify major risk factors for heart disease, including things like smoking and high blood pressure. The advantage is that prospective studies let researchers carefully track what happens over time. That can give us much stronger evidence about how different factors are related. But there's a trade-off. These studies can take years, sometimes decades, and they can be extremely expensive. The third type is cross-sectional. Think of this one as a snapshot. You collect data at one particular point in time, and look at what the population looks like right now. The United States Census is a good example of this idea. Every 10 years, the census gives us a huge snapshot of the population, showing things like age, household size, location, and many other characteristics. Cross-sectional studies are useful because they're relatively quick and they're great for comparing different groups at the same point in time. But because you're only looking at one moment, you usually can't establish what happened first. And that makes it very difficult to make claims about cause and effect. So, 3 different ways to think about timing. Retrospective, looking backward. Prospective, looking forward. And cross-sectional, a snapshot in time. 3 different lenses, and each one comes with its own strengths and limitations. Now here's a distinction that's really fundamental. Every sampling method falls into one of 2 big families, and the difference between them matters a lot. Let's start with the left side, probability sampling. This means every member of the population has a known, non-zero chance of being selected. And we use some form of randomization to make that happen. This is the gold standard when we want to make statistical inferences about a larger population. Why? Because the random selection process gives us a much better chance of getting a sample that represents the population fairly. So, if you want to make a statement like, and therefore, This probably reflects what the whole country believes. You need probability sampling. Now let's look at the right side. Non-probability sampling. This is where some members of the population may have no chance of being selected, or we simply don't know what their chances are. There's no true random selection process. And that creates a major limitation. With non-probability sampling, we have to be much more careful about generalizing the results to the whole population. The sample may still be useful, but we can't assume it represents everyone. So as we go through the specific sampling methods next, keep asking yourself one question. Which family does this method belong to? Probability or non-probability? We're going to start with 4 common probability sampling methods. And then we'll look at one very common non-probability method, the kind you should learn to be a little skeptical of. Okay, let's meet the 4 main probability sampling methods. These are worth knowing well, because they show up constantly, and students mix them up all the time. As we go, look at the 4 cards on the slide. First, in the top left, we have simple random sampling. This is probably the purest form of random sampling. Every possible sample of a given size has an equal chance of being selected. Think of something as simple as drawing names out of a hat, or imagine jury selection, where people are chosen using random numbers. The big advantage is fairness. Everyone has a chance to be selected. But there is one limitation. Just by random chance, your final sample might not represent every subgroup perfectly. Second, in the top right, we have stratified sampling. Here's how this one works. You divide the population into similar groups, and those groups are called strata. Then, you randomly select people from each stratum. For example, suppose you want to survey students at a college, and you want to make sure students from different majors are represented. You could divide the students by major, and then randomly select students from each major. The big advantage is that important subgroups are deliberately represented in the sample. So if those groups matter to your research, stratified sampling can be extremely useful. Third, in the bottom left, we have systematic sampling. This one is pretty clever and usually very easy to carry out. You choose a random starting point and then select every kth person after that. Suppose you have 10,000 people at a concert, and you want a sample of 200 people. 10,000 divided by 200 gives us 50. So after choosing a random starting point, you could select every 50th person. Simple. But there is one thing to watch out for. If there is some hidden pattern in the way your list is organized. Systematic sampling can accidentally produce a biased sample, so always be careful about patterns in the data. And fourth, in the bottom right, we have cluster sampling. Here, we divide the population into groups called clusters. Then, we randomly select some of those clusters and study everyone inside the clusters we selected. Imagine scientists want to study bee health across an entire country. Visiting every location would be incredibly expensive. So instead, they might randomly choose 100 regions and then study all the bees within those selected regions. Cluster sampling can be very cost-effective, especially when the population is spread out over a large geographic area. So there you have it, 4 probability sampling methods and 4 slightly different tools. Simple random sampling, stratified sampling, systematic sampling, and cluster sampling. And next, we're going to focus on the 2 methods that people confuse the most: stratified sampling and cluster sampling. Okay, I'm slowing down here on purpose, because students mix up stratified sampling and cluster sampling all the time. They sound similar, but in a lot of ways, they're actually kind of opposites. So let's line them up side by side, which is exactly what this table does. Start with the first row. In stratified sampling, the groups are homogeneous. That means the people within each group are similar to each other in some important way. In cluster sampling, the clusters are heterogeneous. That means each cluster is more diverse, almost like a little mini version of the whole population. Now look at the second row. With stratified sampling, we sample from all of the groups. With cluster sampling, we only choose some of the clusters. Third row. In stratified sampling, we take some members from each group. In cluster sampling, we take all the members from the clusters we selected. And the fourth row explains why we use each method. The goal of stratified sampling is representation. We want to make sure every important subgroup is included fairly. The goal of cluster sampling is usually efficiency, especially saving time and money when the population is spread out. Look at the examples at the bottom. Stratified sampling would be like taking some students from every single major. Cluster sampling would be like randomly choosing a few schools and then surveying every student at those selected schools. So if you remember just one thing, remember this. Stratified sampling means sampling within every group. Cluster sampling means choosing whole groups and then taking everyone inside those groups. That one sentence can save you a lot of confusion on the exam. All right, now here's the sampling method I want you to be suspicious of. This is our main non-probability method, and it's called convenience sampling. Convenience sampling means exactly what it sounds like. You choose whoever is easiest to reach. There's no true randomization. And that creates a major problem. You generally cannot use a convenience sample to make trustworthy conclusions about the entire population. The sample simply may not represent everyone fairly. Let me give you the 3 examples on the slide, because you've definitely seen all of these before. First, online polls. A website posts a poll, but only the people who happen to visit that website and who feel strongly enough to click on the poll actually respond. So the most motivated or opinionated people can dominate the results, while everyone else is basically invisible. Second, a professor surveying their own class. Imagine a psychology professor surveys only students in their psychology class. Well, those students already chose to take psychology. They may be more interested in the subject than the average student. So that class is probably not a good representation of all college students. Third, mall intercept surveys. That's when someone stands in a shopping mall and stops people walking by to ask them questions. But think about who that misses. People who are at work during the day, people who shop somewhere else, people who don't go to malls at all. And, of course, people who see the person with the clipboard and immediately walk the other way. We've all done that. In every one of these examples, certain groups are systematically more likely to be included, while other groups are left out. And that's the trap. Now, does that mean convenience sampling is completely useless? No. It can be perfectly reasonable for a quick pilot study or for some early exploration when you're just trying to see whether an idea is worth studying more carefully. But you should be very cautious about using it to make a claim about an entire population. So the next time you see a headline based on an online poll, you should immediately ask, who actually answered this poll and who never had a chance to be included? That little bit of skepticism is exactly the kind of statistical thinking I want you to build.